1970, display technology remained primitive. Static imagery overwhelmed early electronic systems. Yet DARPA funded bold computer research. They wanted real-time 3D visual environments. Jet pilots needed dynamic flight feedback. Mainframes filled entire air-conditioned rooms. Overall processing power was extremely limited. Standard screens lacked interactive graphics capabilities. Still, military engineers pushed forward relentlessly.
Mainframe laboratorios la fundamental graphics principles.
This effort changed digital aviation forever. Early flight displays were completely vector-based. Pixel screens were far too slow. Raster hardware struggled with interactive rendering. Instead, electron beams drew lines. Cathode ray tubes projected glowing calligraphic paths. Visuals consisted of bare wireframes. Dark backgrounds surrounded green geometry. Filled surface polygons did not exist. Lighting models were missing completely. Textures were totally absent. Trainees stared at stark outlines. Geometric shapes represented obstacles. Runway boundaries appeared as glowing vectors. Horizon lines shifted dynamically. Frame rates fluctuated violently during flights. Simple horizon scenes refreshed rapidly. Complex terrain reduced speed. Adding multiple structures caused severe flickering. Phosphor coatings faded quickly. Deflection coils worked at physical limits. Vector generators calculated endpoints continuously. Line density controlled screen stability. Excessive geometry triggered heavy refresh lag. Hardware struggled under heavy computational loads. Despite limits, perspective rendered in real time. Three-dimensional spatial shifts matched flight controls. Control sticks directly altered rendered angles. Visuals looked like glowing laser grids. Stark lines cut through darkness. Mathematically, it formed functional space. Coordinates updated dynamically every frame pass. Processors calculated matrix transforms constantly. Clipping routines removed off-screen vector points. Line drivers converted binary math to voltages. Dynamic motion remained smooth under light loads. Pilots perceived real depth in wireframes. Abstract green geometry enabled accurate training. This calligraphic approach bypassed early bottlenecks. Calligraphic displays rendered crisp vectors directly. Pilots interacted through specialized optical systems. Standard desktop monitors were totally useless. Engineers placed CRT displays inside cockpits. Physical mock-ups mimicked real fighter hulls. Heavy optical mirrors collimated light paths. Collimation made lines appear at infinity. This optical illusion simulated real depth. Trainees focused eyes on distant horizons. Pioneering head-mounted displays were tested. Ivan Sutherland built legendary helmet systems. Display tubes were suspended above users. The heavy apparatus required sealing armatures. Mechanical linkages supported massive overhead weight. Sensors measured head orientation during motion. Ultrasonic tracking systems measured spatial angles. Mechanical rods tracked head turns precisely. When pilots moved, vector generators recalculated lines. Line perspectives updated according to head directions. Sitting inside these rigs felt claustrophobic. Industrial control buttons covered cockpit interiors. Hydraulic motion systems shook simulator frames. Glowing vector scopes surrounded trainee seats. Military hardware was pushed to physical limits. Cockpit glass reflected bright green geometry. Pilots wore authentic period flight suits. Physical throttle levers controlled simulated thrust. Analog gauges operated alongside digital displays. Sealed simulator enclosures excluded outside light. Dark environments heightened vector screen contrast. Collimating optics eliminated visual eye strain. Pilots experienced realistic spatial orientation cues. Can bare green lines train pilots? The answer was a resounding yes. Military aviation faced skyrocketing fuel costs. Dangerous training accidents caused severe losses. Real flight hours carried immense financial risks. Human lives were endangered during maneuvers. DARPA realized photorealism was unnecessary. Pilots needed spatial awareness above all. Instrument cross-checking built essential muscle memory. Vector systems excelled at night landings. Low-visibility approaches were simulated effectively. Wireframe runways forced accurate glide slope reads. Trainees monitored pitch angles and speeds. Reflexes were developed without leaving ground. Mid-air emergency training carried extreme risk. Simulating failures in software cost electricity. Traumatic engine flameouts were safely tested. Systems taught reaction timing under stress. Alignment procedures became second nature quickly. Pilots learned digital cockpit feedback trust. Wireframe worlds stripped away visual noise. Attention focused strictly on flight physics. Spatial vectors provided clear positioning cues. Military evaluations proved simulator effectiveness. Real-world pilot error rates dropped significantly. Naval aviators trained carrier deck approaches. Glowing vector lights guided night landings. Flight instructors adjusted parameters from consoles. Simulated crosswinds challenged trainee control skills. Turbulence algorithms pushed pilot stick inputs. Visual cues matched physical instrument readings. Trainees learned spatial disorientation recovery techniques. Repeated runs built instinctual flight habits. Flight schools saved millions of dollars. Jet fuel consumption dropped dramatically nationwide. Aircraft wear and tear decreased significantly. Simulators operated 24 hours daily. Multiple pilots trained every single day. DARPA directly funded their pioneering research. Ivan Sutherland created Sketchpad earlier. He led efforts in interactive graphics. Sutherland developed early head-mounted displays. He partnered with David Evans in Utah. The University of Utah became Graphics Central. Together, they founded Evans and Sutherland. Their company manufactured commercial vector hardware. Flight simulators used E&S systems. Meanwhile, Danny Cohen pursued radical breakthroughs. Cohen worked across Harvard and MIT. He developed real-time networked flight simulators. His system connected over early ARPANET. Computers split processing across distant mainframes. Harvard processed pilot stick control inputs. MIT calculated physics and graphic vectors. Cohen pioneered distributed interactive simulation systems. Packet-switched networks carried dynamic flight data. These researchers solved fundamental graphics mathematics. Clipping algorithms removed invisible line points.
Matrix transformation calculated 3D spatial rotation.
Fast line generation hardware was invented. They were not writing mere software. They invented interactive computing from scratch. Utah produced world leaders in graphics. Their breakthroughs shaped entire digital industries. Computing hardware was massive and power-hungry. Mainframe systems filled large air-conditioned rooms. DC PDP 10 computers formed computational backbones. PDP 11 mini-computers handled specialized task workloads. Memory was measured in small kilobytes. Gigabytes of RAM were purely science fiction. To render 3D space, processors multiplied matrices. Calculations relied entirely on integer arithmetic. Standard central processors were far too slow. Graphics math overwhelmed general-purpose CPUs. Engineers built custom hardware coprocessors instead. The Evans and Sutherland LDS-1 led hardware. Line drawing system 1 handled matrix math. This specialized hardware relieved main CPUs. Dedicated vector generators drew lines directly. Magnetic core memory held coordinate points. Woven copper wires stored binary flight data. High-speed digital to analog converters drove displays. Software commands became high-voltage deflection signals. CRT deflection coils steered electron beams. These mainframes consumed many kilowatts of electricity. 1970 DARPA initiatives never targeted entertainment. Yet their breakthroughs revolutionized modern computing. Wireframe runway algorithms formed modern rendering pipelines. Vector line math enabled complex 3D graphics. Specialized vector processors evolved into GPUs. Graphics processing units trace routes to LDS-1. Distributed flight tests over ARPANET pioneered networking. Multiplayer online environments used Cohen's principles. Cloud rendering architectures rely on distributed processing. Modern civil aviation safety depends on simulators. Commercial pilots train in descendant mainframe technology. Virtual reality headsets descend from Sutherland's HMD. Modern video game engines run early mathematics. Every real-time pixel pipeline traces back here.